All right, hey everybody, Mr. Fortin here. Happy Thursday. Asynchronous problem set. Now I know what you might be thinking. I'm doing this section 6-6 problem set. I didn't get a lecture. Where's my lecture? I know you love the lectures, right? So anyways, guys, you should already know about this. Section 6-6 is simply the sine and cosine ratios. And it's all about, we've been talking about SOHCAHTOA already, of course. Of course, is the sine of a particular reference angle. Guys, this is all straightforward. This is going to be like a 2-minute video, okay? I'm not really going to lecture here. So take it if we have this as our reference angle, right? 26 degrees here. The sine of this 26-degree angle is going to be this, our opposite. Oh, I can't really write that well. Here's op. That's a P. This is another P. Oh, over the hypotenuse, okay? Over the hypotenuse. You've seen that. You've known that. You love that. That's hypotenuse right there. So on these problems, I can't really write on PDFs that well, but on these problems here, you might probably want to draw them out and label up the sides real quick. That can save you some time. So anyways, sine of a particular reference angle, sine of 26 degrees is that unique ratio of x over 17, and that's equivalent to whatever your calculator says here. I've overheard you guys here. How do you know that's in degree mode? Well, you're not going to see radian. Okay, if you see radian here, it's in radian mode. We don't want that. You want it in degree mode here. So just anyways, what's the sine of 26 degrees? Well, it's certainly less than 1 because the opposite is definitely larger than the smaller than the hypotenuse. So x divided by 17 has got to be less than 1. So let's see specifically what x over 17 would have to equal. Sine 26, what are we doing here? 26 degrees, sine. Okay, anyways, sine. So more of this here, cosine. So anyways, we've been doing the lessons on Desmos. You haven't had any formal lesson for this because you should know what the sine of a particular reference angle is. You should know what the cosine of a different reference angle is. That is the adjacent over hypotenuse ratio that you have there. Okay, so I'm filming this video to show that this information is in the textbook. There we go. It looks like a J. It does look like it. Here's my adjacent side, right? We got a reference angle here. It's not the hypotenuse that's part of that angle, right? Hypotenuse is part of that angle. That's the hypotenuse side. It's the other side. It's the leg. This is the adjacent leg. So label it up here. And in fact, they've shown it here and just reiterated to us. And now you have 3 trigonometric ratios to play with in case you're just like, well, what do I have to play with now? And you've forgotten here. You have the tangent, you have the sine, and you have the cosine, okay? Or the order that we typically go would be sine, cosine, and tangent. That's how the buttons on your calculator go, right? Check it out. Sine, cosine, and tangent. SOHCAHTOA. Know it, love it. Don't make me look bad in future classes because you don't know what SOHCAHTOA stands for. So, S-O-H, sine, a particular reference angle, is the, what's the O? Opposite over hypotenuse. Yeah, we're going to use that ratio. Right? Cosine, a particular reference angle, is adjacent over hypotenuse. This is stuff you should be practicing. This is stuff you should try to get quick at, doing them faster, as Ms. Yip said in the class today in 5th block as well. And then finally, TOA, right? Opposite over adjacent. That kind of thing here. Any reference angle. So they're saying that's the reference angle. This is the opposite leg. This is adjacent leg. What are my reference angles up here? Well, it's complementary to that one. Well, then all of a sudden this becomes the opposite side. That becomes the adjacent side. It flips. And therefore, the cosine of a complementary angle is equal to the sine of the original angle. Something like that you learned on Tuesday's lesson. All right, there we go. SOHCAHTOA. So, S-O-H. Hey, let's actually let me highlight it here. Because I guarantee you there are people like, why does he keep saying SOHCAHTOA? What does that mean again? The sine of a particular reference angle. All right, here, I'm not even labeling it down here. Sine of a particular reference angle equals the opposite over hypotenuse ratio. Thought I was highlighting. Not highlighting. There we go. Opposite over hypotenuse. Sure. Ca is cosine equals, come on, ca, C-A, right? The A is, that's the numerator here, is always going to be the adjacent or opposite. It's not going to be hypotenuse. And then, so, ca, hey, TOA. Just a way to remember, to know this stuff. TOA. There's my TOA, not TOA. T-O-H. Remember that I made the mistake we talked about it earlier. Okay? So what you're doing on this assignment, guys, what you've been doing the last freaking days, spend 1 to 2 minutes each question. That's it. And this should be like a 20-minute assignment, I'm hoping. But spend up to 40 if it takes you time. That's what I say here. You got an asynchronous block. You can start this for classwork, finish it for homework. Guys, there's lots to do. I don't want you to be way behind when you go to future classes. So anyways, that's why I put in those 40 minutes now. Just do it, okay? So that you breathe a little easier in future classes you take, okay? Sine of 67 degrees. Well, there's my opposite over adjacent would, sorry, not opposite adjacent, would be tangent. So sine of 67 degrees, well, that's so opposite over hypotenuse, x over 120. There we go. You could solve something like this. Cross multiply, right? Or multiply both sides by 120. 120 times by the sine of 67 degrees. You can get that on page 271, right? Sine, cosine, tangent. Those are on page 271 too. Check it out here. Look at that. Sine, cosine, tangent. You got everything. Just integer values for the angles, though. You don't have like 1.5 degrees or so. So you have an approximation there. So if possible, use your calculator for this. It's just going to be more precise and less rounding. So you'll get something more precise than even their 110 you have here. Okay? Go to 1 decimal place. Go to 2 decimal places. I don't care. You just need to think through it. Okay? Cosine is 67 degrees here. Well, cosine is 67 degrees is my adjacent over hypotenuse. Say, you guys all know this. Why am I showing this to you? Okay? Keep in mind here, too, we just had one lesson on inverse tangent. This actually might be an important thing, is how to do a problem like this. Okay? Sine of n degrees equals 22 over 40. How you might do that in a calculator. And it's going to work just like the inverse tangent did here. Okay, so check this one out here. I got the n degrees right here. I already know. So here, I don't know the angle. So this is a great question I got near the beginning of our unit. Well, what if I know the sides, but I don't know the angle? How do I get the angle? So I know what you're thinking. Maybe I can use inverse tangent. No, don't use inverse tangent because we've used inverse tangent before. You could use the Pythagorean theorem, solve for what this is here, and then just use that tangent of -1 power equals 22 over whatever you solve for there. But hey, you're working too hard, okay? So much like tangent, which has an inverse function, inverse tangent, the sine and cosine have inverses, right? Meaning you know the sides, right? So here we know the opposite side. Wow, look at this. I can't write any more precise than this on a PDF. This is my opposite side. This is my hypotenuse here. So I know those sides. So I should be able to, if I know the side, I should be able to get the freaking angle because every angle has a unique sine ratio that's specific to that angle. So if I know what the ratio is, I can use the inverse sine to get the actual angle. Does that make sense? I don't know. But a calculator, right? A calculator would be able to, for a particular angle, spit out a decimal that is 22 over 40. So why not, if we have the 22 over 40, get the actual angle? That would spit out 0.555 for us. So anyways, 22 over 40. This is how you do a problem like this. We want to know the angle. Well, here we're going to use the inverse sine because right? We have the opposite side. We have the hypotenuse side of the particular reference angle we're trying to get. So we would do 22 divided by 40. That's the sine ratio of a particular freaking reference angle. We just need to figure out what the reference angle's measurement is, right? When you get that, when you solve for the angle, we have the sides to get the angle. So here, what we're going to do, we're not going to do sine of 0.55. That would mean sine of 0.55 degrees. That doesn't make any sense. The opposite over adjacent ratio is opposite over hypotenuse ratio is 22 to 40 or 0.55. This is 55% of that one right there. Okay, so what we're going to do is we're going to back it up. Beep, beep, beep. I'm going to hit the second button, and I'll hit sine to the -1. Okay, because the idea of this is, right, I'll go over here, maybe I'll do this here, right, sine to the -1. Like, this is what you're telling your calculator, right? Means if I have a 22 to 40 ratio of opposite over hypotenuse, right, opposite over hypotenuse, I can use that's a particular sine ratio of a particular angle. I can use that to solve for that particular reference angle measurement. Does that make sense? In this instance here, it's n degrees, okay? That's what I'm trying to get here. So I simply got to do this. I got to use the inverse sine, similar to the inverse tangent used before. So I'm going to hit sine to -1 and boop. Mathematically, we get 33.4 degrees. But it looks like they asked you to round this here. Oh, there's Mr. Chu. What's he doing there? Okay, 33 degrees. And there's the answer, okay? So check it out. Here it is. Quick thing. Bang through this, guys, here. I think you got to do what? Number 3. That ain't hard at all. But it's just to remind you that every angle has 3 of these ratios, okay? Sine of A, that's going to be 21 over 29. Cosine of A, that's going to be 20 over 29, okay, right? Yeah, people make mistakes, it's fine, but, and then B, angle B, its sine is going to be 20 over 29. Its cosine is going to be 21 over 29. See, it's just the opposite, right? Its complementary angle is here. So that's another reminder there. Its tangent is going to be what? 20 over 21. There we go, okay, that kind of thing here. So you're doing those 2 problems. You're doing a few more of these. What do I got here? Show it to me, okay? Let's see what we got here. Our homework is the Thursday homework. Nobody's done it yet in 7th block. Somebody's done it in 3rd block, though. I saw that. Let's see, we're seeing names. We shouldn't be seeing that here. We got this. Okay, this is what you're doing. Yeah, I just did number 3, number 6 for you. Number 9 is not bad at all. State 2 different equations here and use to find the value of x. What can I do? Oh, easy. Cosine of 55 degrees equals x over 79. I can solve that. Do you have to solve that? No, just set it up. Sine of 35 degrees equals x over 79. There we go. Not bad, not bad, not bad. 11. State 4 different equations. Wow, it's a lot of equations you can use to find the value of x. But hey, you have 2 different potential reference angles. And you have all the other sides here. So sine of 48 degrees equals x over 265. Cosine of 42 degrees equals x over 265. And then you use tangent. I don't know. You'll figure that one out. I'm just kind of doing it all for you. 12. Quick problem. Hey, that's connecting. Cosine, complement sign. Explain using the diagram here, okay? And, ooh, some tricky problems. You got number 13. Come on, go back. Oh, there we go. Number 13. Hey, y is the sine of 30 degrees. Exactly 0.5. That's one of the sine values we know exactly, right? We didn't know, like, if I had sine of 33 degrees, for instance, we just had 33 degree one earlier. I want the second, but I want the regular sine. Not a number. Look at that. If I had 33-degree angle, I take the sine. Hey, it's going to jump out a whole bunch of gibberish. But, like, it's kind of an irrational number. It'll go on forever. But actually, sine of 30 degrees, 30-degree angles, there's a specific sine amount. Right? We get a particular value here. Why is that? Explain using this diagram. What do we know about a 30, 60, 90-degree right triangle? Yeah, check it out here. 30 degrees, we're in degree mode because it says radian. It says radian there, no good, no good. We want a degree. Yeah, we don't see anything there. Assume we're in degree mode. I'm going to hit sine, I get 0.5. So I actually get a rational answer there. A rational answer, a rational number. 1 over 2 is the answer. Why is it 1 over 2? So J to K is in a 1 to 2 ratio. Why? You explain, you think back to something that we talked about before spring break here, okay? What else we got here? 14, 16. Yeah, this is easy enough. That's inverse sine. So sine to negative 1 power of 15 over 17. Boom, calculator should give it to you. What else we got? 16. Hey, that's a good question. Hey, somebody's gonna explain that. I know this is a tough thing to explain, but hence, what's the largest side of a triangle? Right? Are the legs ever large of a right triangle? Are the legs ever larger than the hypotenuse of a right triangle? Why is Mr. Fortin yelling so much today? Okay. All right. Anyways, then you got numbers 5 through 17 all. You can skip 3 of the problems though. You don't have to do 7, 10, 13, right? Some of these are a bit longer. This takes a little bit more time. Anyways, you guys got it. I have faith in you this time here. Oh, some tricky problems. Trig, baby, trig. I'm not going to go over anything else. I mean, I think like number 11 and 12, isosceles triangle. Remember, the isosceles triangle, if you drop an altitude, it's going to create 2 congruent right triangles next to it here. So that might be something that you have a little trouble with. Number 11, the base of an isosceles triangle. Do you have to do number 11 even? Yeah, you can do number 11. Base of isosceles triangle is 32 meters long. Legs are 24. So let's maybe sketch this one out so you have this as an example. Here, I gotta undo this. Get rid of that here. So number 11 is one that I'm doing right here. Okay? The base, oh, come on, let me draw. What? I hate you. I hate this writing on PDFs. Well, it's the fact we have PDFs. It's kind of cool in our lives. All right, let's do this. This is 32. Can't even label that. 32. Okay? Legs are 24. Well, we know no. Something like this. Can't really write on this. All right, well, we know if this is 24, mess. Hey, the key to this problem, I'm trying to draw where it's going to let me draw, but it's not letting me draw. There we go. Key to this, if I drop an altitude right here, those 2 triangles are congruent by what? This is a leg congruent to itself. The hypotenuse, they're congruent by HL, congruent by HL. So that means that this is the length, this is 16 right here. That's what I'm trying to say. This is driving me crazy. That would have to be 16 right there. The legs are 24, so there's 24 right here. What is it asking here? Find the measure of the base angle, okay? So then you can use inverse cosine, this being 16 and that being 24. Anyways, sketch it out. You need to spend more time on this problem than I just spent on it right now, okay? Because you're the student, right? Trying to get this. Fine, you want me to see it? You want me to do it out? Fine, I'll do it out on a different sheet of paper. This is number 11, okay? Number 11 right here. Look, an isosceles triangle. Pretend these are the same here. This is 24. This is 24. This is 32. I just know because people ask this here. Right? I don't want to piece this together on your own, right? Sometimes it's hard to figure something out on your own. This is 32 right here. The way, this is it. When we get one of these reference angles, remember the base angles of an isosceles triangle are congruent. That's the ITT, right, that we learned in chapter 3. So what we have here, chapter 2 was it even? Forget. But anyways, these are the same. This is what we want to figure out. Okay, this is our question mark. What's that reference angle? Well, hey, remember, I can drop an altitude down because through a point outside of a line, there's exactly one perpendicular that can be drawn. Heck yeah. Okay, so now I have a right triangle, right? I have a right triangle here, and I have a right triangle on the left side here. I'm not going to mark that because we're going to focus on this one here. What do I know? It's congruent by HL because you know what? This leg is congruent to itself, and that's not triangle, that's not triangle. It's a right triangle, hypotenuse is both congruent by HL. Perfect. So that means CPCTC, this side is congruent to that side. Remember, the altitude from the vertex of an isosceles triangle perpendicularly bisects the base, right? That's something that we know. It's a median. Anyways, it'd be the same length here, okay? So if this is 32, this is x, and this is x right here. 2x would equal 32, so what's this length? It's 16. Okay, it's 16. So there's lots to think of here. So now we have this. Man, there's kind of a lot to do in this problem here. We'll talk about this right triangle right here. And what do we know about it? Well, we know its hypotenuse is 24. We know it's, right, if this is our theta, this is what we got to figure out. That's our goal in this problem, is to figure out the measure of the base angle, right? They're the same both here. We have the adjacent side here is 16, okay? What do we know about adjacent and hypotenuse? Well, that's going to be part of the what ratio? The cosine ratio because of ka. So ka toa, okay? So cosine of the reference angle equals 16 over 24. How can I solve the problem then? Well, I can use the inverse function, similar to how we use the inverse tangent the week before spring break. I can use inverse cosine of that 2 to 3 ratio, right? Or 16 over 24. And that's going to tell me what theta is. It's tell me what the angle is. And let's just do it in our calculator to go ahead and get it. We got this. We got, 16 over 24. All right, it is 2 to 3, but we'll do it here. And then we'll do that. Hit the second button. Okay, we know the sides adjacent to hypotenuse is in a 2 to 3 ratio. What must be the angle that goes with that unique ratio right here? And it's going to be this. 48 degrees is your answer to number 11. Drop the mic. You did it there, so maybe that was a worthwhile example. I shouldn't take it for granted that you would be able to figure that one out, right? Which I never do, right? You always can review with the jam boards, right? But you got to be taking risks. It's not my job to take risks. It's your job to take risks, right? There's nothing more risky than never taking any risks, isn't there? And there's no risk in geometry because the worst thing happening, you're going to be wrong, and that's fine. You move on with your life. Not going to affect your life really all that much here. Okay, 48 degrees is your answer for number 11. Thank you guys for watching. Have a pleasant Thursday. Take care and message me if you have any questions.